with the Fibonacci numbers, and all these are examples of sequences, which is what we're going to study today. Now, the cool thing about sequences is that we can use them to describe a lot of stuff, and our goal right now is just to get used to a lot of notation. This whole section is really getting used to notation and understanding different things about sequences, how to write them, how to add them, etc. Now, for instance, in this first one, it's called an arithmetic sequence. We'll study more about that in section 12.2. Can anyone tell me what the next term in that sequence would be? What would I expect next?
17.
Yeah, 17. You're just adding 3 to get from one term to the next. How about the Fibonacci sequence? Can anyone tell me what the next term is here?
21.
Yeah, 21. And to get from any position here to the next term, you're going to add up the previous two terms. So 8 and 13 gives me 21. 13 and 21 gives me 34. And then 55, and so on and so on. Now, the thing that I need to help you with in this example is to understand some of the notation here. There is one more notation that we can look at, and that would be this one down here, this factorial sequence. So the first term looks like this: 1, 2, 6, 24, 120. Can anyone tell me what the next term would be? Johan?
720.
720, well done. So what these numbers are factorials. So for instance, let's take a look at the fourth term here. This is the first term, I'll call it a sub 1. That's a sub 2. Here's a sub 3. This is a sub 4. So a sub 4 is really a sub 4 is really 4 with an exclamation point next to it. Now, in a math class, that means 4 times 3 times 2 times 1. So that's your 24. All right, don't steal my thunder. This is my show. Okay, but she's right. If this was an English class, this would be 4. All right. Yeah. All right. So you know some of my material. All right. Good on you. This is a number that gets really big really fast. For instance, if I wanted to calculate 10 factorial, I'd probably lose interest in doing 10 times 9 times 8 times 7 times 6 times 5, etc. Your calculator can do that. So let's find that key on our calculator. I got to change a couple things here for myself. But type the number 10 and then go to the math key, the math menu, and instead of staying right on this math menu, you're going to go over to probability. Is there something that looks, handy down here? Yeah, fourth one. All right, so 10 factorial. Now, an interpretation for factorial is it's the number of ways you can arrange a group of n objects. So in this particular case, 4 factorial, there's 24 ways that I can arrange 4 objects. So for instance, if I had 4 students and I wanted to put them in one row of chairs, and I have 24 choices as to how I could order those students. 10 factorial, that's pretty big. I mean, consider that you only have 10 objects. If you're trying to line up the starting lineup and maybe the manager of a baseball team to listen to the national anthem, you'd have 3,628,800 different ways you could arrange them along the path from home to first base. That's a lot. And in fact, your calculator would choke if you tried to do 70 factorial. It'll be too big. So basically, 70 factorial is bigger than 10 to the 100th power. So, wow. It's a number that gets really big really fast. You use it in probability to calculate things like, how many winning lottery tickets there are, those kind of things. But we're not going to worry about those applications right now. Right now, I want you to understand this notation. So typically speaking, we'll give a sequence a name with a letter. maybe A or V or U or whatever letter you want to choose. And then the individual terms get subscripted. So the first term is A sub 1, the second term is A sub 2, A sub 3, and so on. And what I'd like quite often in these sequences is the general term. And in this case, the general term is n followed by a factorial. So that's the general term here. We can come up with general expressions for these other sequences as well. So let me find this right here. Let's call this sequence B. I could call that B sub 1. This is B sub 2, B sub 3, etc. If I wanted a general term, I could write that general term like this. B sub n would be 2 plus n minus 1 times 3. Now you could simplify that and rearrange it a little bit, but you'll see after section 12.2 that there's reasons to write it like this. If I put in a 1, 1 minus 1 is 0, times 3 is still 0, plus 2 is 2. If I put in a 2, I end up with 1 times 3 plus 2 is 5, and so on. This is the general term for this sequence. Fibonacci sequence, well, that's going to require a little bit more work, but you know, it's doable. It's doable. Let's see here. Let's take a look at this next one down. So this next one down gives you an expression for the terms of a sequence. So it's a sub n equals 4n minus 4. And let's see if we can't find the first few terms of this sequence. For instance, they ask us for a sub 1. A sub 1 means you're going to put in a 1 here for n. So 4 times 1 minus 4 is going to be 0. A sub 2, well, here you're putting in n equal 2, so 4 times 2 minus 4 would be 4. And let's do 2 more. You're asked to find the first 4 terms and then the 100th term. So a sub 3 and a sub 4. Now after you get up to a sub 3, you might start seeing a little bit of a pattern here. 12 minus 4 is 8. 0, 4, 8. What's the next one? 12. Pretty easy on that stuff right there. All right, this is just an arithmetic sequence. You're adding 4 to get from one term to the next. Okay, but how about a sub 100? So a sub, let's put that here, 100. Any takers on that one?
396.
Thank you. 396.
Oh, wow, hater.
All right. So the first 4 terms and the 100th term. Okay, looking pretty good. Looking pretty good. Let's move on down to something that if you've taken some programming languages like C++, then you've probably seen some recursive programming. And that's what we're going to look at right here, is a recursively defined sequence. Recursive programming is very powerful. It's not really easy conceptually, but it is pretty powerful. So this is example C and D. This is where you're going to want to have your calculator available. We're going to start out by doing the first one kind of by hand, and then we'll maybe repeat this with the graphing calculator. Show you how to do some of these things on that. A sub n is given as 2 times a sub n minus 1 plus 3. And then there's also a note, and a sub 1 equals 4. So let's unpack this a little bit. What does this all mean? What they're doing is they're telling you how the next term is defined in terms of the previous term. So for instance, if I wanted to figure out what, say the second term in this sequence was, let's say a sub 2, and let me put that 2 in here. Then what this rule is telling me is that I've got to take 2 times the previous term. That is, in other words, 2 times a sub 1 plus 3. So let's squeeze that in here. Equals 2 times a sub 1. That's your 2 minus 1. So a sub 1 plus 3. Well, what's a sub 1? 4. So this is really 2 times 4 plus 3. I'll write it. 4 plus 3. So 2 times 7 gives me 14. Great. Now if I need to find the next term, say the third term in this sequence, a sub 3, I can do that because I now know what a sub 2 is. So a sub 3, like before, we're going to look at our previous term in the sequence. It's going to be 2 times a sub 2 plus 3. 2 plus 3 equals 2 times, well, a sub 2 was 14. So it's going to be 14 plus 3, so 17. 14 plus 3, and 2 times 17 is going to be 34. All right. So, I mean, it has some conveniences, and it can be useful, but can anyone see a problem that I might run into if I needed to figure out a sub 100 like I did with the last sequence?
You have to know what is a sub.
Yeah, you'd have to go through everything. You have to go through a sub 3, a sub 4, a sub 5, all the way up to a sub 99 before you get to a sub 100. You don't have what's called an explicit expression for this. You have to get the previous one to know the next one. Yes, sir.
So A1 is.
A1's
I
given.
guess I don't get where you get 14 from in the third one, because it's A sub 2, but.
A sub 2 was 14. We calculated 14 in the second one, right? So I took the a sub 2 from here, and I put it into here and said, okay, well, that's 14. I just figured that out. Now that I know that that's 14, I can use it to get a sub 3. So let's do one more here.
I see.
All right. All right. No worries. No, I appreciate the question.
Thought there was-
So we got a sub 4. And to know a sub 4, what would I need? What am I going to tap into?
A sub 3 plus 3.
A sub 3 plus 3. All right, so that's going to rely on a sub 3. A sub 3 is 34. Let's put that in. 37 times 2,
74.
74. Nice. Nice. So 74.
C says the bar thing.
Yeah, to the deaf mute, yes. All right, so this is kind of tedious. So it'd be nice if we could get our calculator to do this, and we will. We'll practice that. On your handout, there's some commands that are going to do just that, is help you do a couple things. First of all, you have to change your mode, and then you have to input your function, etc. But let's do this other one at least a little bit by hand first.
Question,
Yes.
is it not going up by like a sequence though?
No, it's
Because
not.
Did it not go up by 10,
Right.
and then it went up by 20, and then it went up by 40?
It's just this relationship. It's hard to predict what this is going to look like in the long term, but it's going to start out a little bit slow. It feels like it's going up almost exponentially, but I'd have to look at this and spend some time graphing it.
Because
So then one, the next one will go up by 50?
yeah,
Well, every time you're more than doubling it, right?
Yeah, but
So you're taking the previous one, you're adding 3, and you're doubling it. So it does go up like exponentially and then some. So it's increasing pretty fast. Yeah, so our next one's gonna be what? 77 plus, or 77 times 2 is gonna be 154.
I think it is going back up because it's 10, then 20.
Yeah, that's what it is. It seems like it's going up.
It's 7,
You know, I'm just trying to find it easy.
Yeah.
Remember it.
The next one you add,
You know,
Because it seems
you don't wanna memorize it because I could throw you completely off base by just changing that to a 2 or a 5 or a 1.
Why would you want to do that?
Cause I'm mean.
Why?
I'm kidding, I'm not mean, but no, the idea is to learn it, not to memorize stuff. So, let's try our next one. So there was two examples in here. The next one is this one, a sub n equals 1 over a sub 1, or 1 over a sub n minus 1. So let's write that down, a sub n equals 1 over a sub n minus 1. Now, when they give you a recursively defined sequence, they have to tell you the first numbers here. So in this case, a sub 1 equals 2. So let's see what that implies for us as we work through this example. Let's see if we can't find a sub 2, for instance. So a sub 2 is going to be 1 over what?
2 and
1 over
2
a sub 2 minus 1.
2 minus
So 2 minus 1 is 1. So it's really 1 over a sub 1, which is 1 over 2. All right, so let's go to a sub 2 now.
Huh?
Angel? So we know what the first one is. So to get the second one, to get a sub 2, I put in a 2 here. What's 2 minus 1? It'd be 1. So this is really, when this is 2, this is a sub 1. And a sub 1 is given to us as 2. So this gets replaced by 2, and that's it. There's no more simplification we can do. A sub 2 is just 1 over 2.
I think I do.
Okay, just, let's.
Let's try another one.
Keep going.
Yeah.
All right, so let's try another one. A sub 3 is going to be 1 over what?
3.
No,
3 minus 1.
1 over a sub 3 minus 1. I'll actually write it out here. You've got that 3 there, 3 minus 1. All right, without your graphing calculators, help me out. What's 3 minus 1?
1 over 2.
1 over a sub 2. But we know what a sub 2 is, right? What does a sub 2 equal?
A sub 2 equals 1/2.
1/2. So let's put that in here.
Bro. Oh.
So now let's.
1 over 2.
Oh my goodness.
It's a quarter though.
So it's just, so you just really
No, it's a.
solving it.
So each time we get 1, we can get the next one. So I started out with a sub 1. That allowed me to find a sub 2.
Okay.
When I have a sub 2, now I can find a sub 3, because a sub 3 is just a reciprocal of a sub 2. What's the reciprocal of 1/2?
2.
2. And now I can find a sub 4. A sub 4 is going to be 1 over 4 minus 1, or a sub 4 minus 1,
Which is gonna be a sub 3.
which is 1 over a sub 3.
2, so it'll be 1 over 2.
We're back to 1 over 2 again.
Okay. Don't piss me off.
Well-
You just jump like that.
It's all the same thing.
Yeah, so,
Don't keep.
so a sub 5. Do we really have to do a sub 5 by hand? What are you going to get when you do a sub 5?
What
It's
over a
just
sub
gonna be-
4?
Well, what's multiply?
You're gonna get 2 again.
Reciprocal.
You're going to get 2 again.
1/2.
It's just going to bounce back and forth, 2 to 1/2, 2 to 1/2, etc.
So does that go between odd and even, like? Or
Yeah.
Right,
prime
because
and
it
not
seems like
prime?
So it's kind of strange. But here, let's play around with it in a couple different ways. take out your calculator. I want to show you how to do this on your calculators. So you can feel like you're getting this, you're not going crazy. Let's start out with the first one that we had right here, the first recursive sequence we got. And there's a couple settings that we're gonna have to do on your calculator to get things up and running. So the first setting that I want you to adjust is the mode. You hit the mode key, and you're gonna go down to where it says function, and then across till it says sequence, S-E-Q, and press the enter key there. So you want it to be set to sequence. Now that's gonna mess with your calculator in strange and untold ways, and we'll see that. Does everyone have that change made? Mina, good? No?
I'm sorry.
So go to mode, and then go down to this line here that says function, go all the way across and press sequence.
Got it.
Everyone else good on that? All right. Now, let's get out of here so you can hit the clear button to exit your mode key. And now let's press the Y equals key and see something totally different and unexpected. Whoa, mind blown. All right. So you get this U sub n. Now that U sub n is functioning like our A sub n. They're just using a different name for their sequence. So this is really the A sub n. Now if I'm going to write this first example in terms of U's as opposed to A's, it'll be U sub n equals 2 times U sub n minus 1 plus 3. So that's what I'm going to write here and help you write on your calculators. The first battle is to find U, and it's right above the 7. So what am I going to have to do to get that U right above the 7? Second. So I'm going to want 2 times parentheses, and then let's go to that U. Second, and then 7. So 2 times parentheses, and then go to your U, second and 7. You can see the keys that I'm using on the bottom here. And then I want n minus 1 in parentheses. So let's type the parenthesis next. And here's what's going to trick you out a little bit. Forever and a day, you've always been pressing this key to get an X. But if you notice, it's got X, T, theta, and N. That's for function mode, parametric mode, polar mode, and sequential mode. When we press this now, instead of getting an X, you get an N. So we want n minus 1, close parenthesis, plus 3. And then close parenthesis again. So, cool, great. There's one last thing you're gonna need to do here. That tells you your general term. You've gotta tell it the first term. Now, if you've got an older calculator, it might say U sub min. If it doesn't, if it says U sub 1, that's where you're gonna type in the 4. That 4 is coming from the problem itself, where it says the first term was 4, and then this is the general term. So that's the things that we've just put in. We put in the general term for U sub n. The first term was U sub 4. We all together here. Hannah, doing okay? Brian?
How did you get to that screen? I missed it.
You hit the Y equals key. So it's the Y equals key. And of course, now that we're in sequential mode, it should look a lot different.
It looks different than that on my app, so I don't know.
Yeah, I'm not sure. It might, I mean, you can borrow a calculator if you'd like. Might be advantageous. I'm not sure what's going on with the app. They're usually pretty good. In any case, let's just double check that our window settings are correct, or our table settings are correct. Hit the second key and then the window key. Make sure that independent is set to ask and dependent is set to auto. So with those settings, we should be good to go to our little table function. So everyone got these settings okay? We're good on those? Hit the second key, then the graph key, and that'll take you up to table. Here's the cool thing. Now you can just let your calculator do all the work. So you put in a 1, it tells you the 4. It's like, okay, well, I knew that. You put in a 2, it gives you the 14, 3, 4, 5. You can even jump like up to 10. So it's kind of cool. So pretty nice to be able to do that. Yeah, it grows big really fast. I think this is growing more than exponentially. In fact, it is, because 2 to the 10th power would be 1,024. So it's growing faster than exponentials. All right, let's see about plugging in this one. This one is kind of defined for you a little bit on your handout. Yes.
Definite, like, are these two definite equations that we're gonna want for, say, questions on a test?
Well-
Just depend on, how you set up the problem.
So what's going to change is the format of these equations. They can change a lot. So it's not like you have to save them or should save them. Those are going to change a lot. You could actually write your arithmetic sequence. I wrote it like this. This is an explicit formula. If I wanted b sub 1,000, I could get the 1,000th term really easily. But I could also write this recursively. So I could write it as b sub n minus 1 plus 3. Just take the previous term and add 3. So that's a recursive version of this same sequence. Now this does have some advantages, but the advantage of this is that I can get any term I want anytime I want. I don't have to find the first 1,000 terms to get the 1,001st term. So on the test, I'll try and be explicit and say, if I want a general formula for a term, I'll try and be explicit and say, I don't want a recursive formula. So that would eliminate that kind of answer. Let's look down at the second of these examples. So the commands and all that stuff are on your handout in case you want to practice this at some time later, including our Windows setup, which I'll just borrow there recklessly. So if I want to do this one, let's go back to our y equals key. Let's clear this out. A sub 1 for this example was what?
1/2.
Nope.
No, 2.
2. A sub 1 was 2. And then I need to type in the expression 1 over a sub n minus 1. Well, instead of a's, we're going to use u's. 1 divided by u. So you have to hit the second key, then the 7 key. 1 over u sub parentheses n minus 1. Bam. Like that. So now I'm all set. But we're going to do something a little different with this one than we did with the first one, which is to graph it. So as far as graphing it's concerned, I'm just going to steal the window settings that I had on our handout. So that was these window settings. And min to n max is 1 to 10. It's got x min and x max, y min and y max. Actually, I guess I'll think I'll make one change here. I'm going to make that a 0. Now, if you're looking like, oh, I can't keep up with all these changes, here's a quick fix for what you might want to do. You can hit zoom 0, and your calculator will give you a pretty good, and not perfect, graph of your problem. But if you look at it, it's like kind of hard to understand because you've got stuff up here, stuff down here. So I'm going to adjust my window a little bit. I'm going to make x min 0, x max I'll leave at 10, y min at 0, and y max at 2.5. Your graph doesn't have to be perfect. That's fine. There's your graph. And you see what we saw when we were looking at this problem. That is, these values are alternating. You go 1/2, 2, 1/2, 2, 1/2, 2, etc. So if you have an odd term, you get a 2. If you have an even term, you get a 1/2. So pretty easy. But let me show you one last little trick about this. If you wanted to look at these plots and figure out what your terms are, hit the trace key. And there you go. At n equal 1, y is 2. at n equal 2, y is 1/2, and so on. And it just alternates. So you can trace this and get all the values of the function that you need. So it's just as good as the table function, except you've got the visual aspect of having this plotted as well. So kind of nice. You know, it's not imperative that you be an ace with the graphing calculator on this stuff, but I do want to show you that you can get your money's worth out of your graphing calculator. All right. What do you need?
Can you go back to the word?
To this part?
Yeah.
Yeah. All right. What we're going to work on next is trying to come up with our own formulas for stuff like this, except we're not going to try and come up with recursive formulas. We're going to come up with explicit formulas. Let's start with example E. Rats. Let's see, so example E.
Should we turn up standard form for all intents and purposes, or for this chapter, should we just leave it out?
You know, standard form's pretty handy sometimes, but you know, Zoom Fit will always give you at least a good place to start with your graphs. All right, so let's look at example E. You've got a sequence that looks like this. We've got 5/6, 6/7, 7/8, and 8/9. Let me go back and remind you some of the notation here. So this term was a1. This term is a2, a3, a4. So I'm calling this sequence A, and I'm subscripting it with these numbers to correspond to each of these terms. And it might be helpful if I wrote a4 there instead of a3 twice. All right. So what I want is I want a general term for this. I want to know what a(n) looks like. So, let's think about that a little bit. Now, your clues here, you're going to have to start looking at the index of this and comparing it to these things up here. And do it in two parts. You know you're going to have a numerator and denominator. So start out by comparing the 1 with the 5, the 1 with the 6, the 3, or excuse me, the 2 with the 6, the 3 with the 7, the 4 with the 8. And when you compare these numbers to these, can you see a way to get from here to here, the numerators? I'm not worried about the denominators right now at all. How do you get to the numerator? Adding 4. So in general, you're going to take this number and add 4. Now over here, that's going to be your n. So it's going to be n plus 4. That's how you're going to get these numerator terms. How about the denominator terms? What are you going to do for the denominator terms?
It's gonna be like u plus, or no?
Add a 5.
Yeah, you're adding 5. What am I adding 5 to?
N plus 4.
You're adding 5 to whatever this is. So, like here, you've got a 3, add 5, you get 8. 4, add 5, you get 9. You have an n, add 5, you get n plus 5. That's your general term for this sequence. So with this, I can get any term I want now because I've got the general form. So, you know, maybe Kyle's got a birthday in May or something like that. He wants to put in a 5 here. We can, oh, January?
May 1st.
May 1st? All right. So put in a 5 here. You get 5 plus 4 is 9. 5 plus 5 is 10. The fifth term would be 9/10. And you can kind of see that right over here. You can kind of predict what the next term is going to be, but it's nice that you've got an explicit expression for this. And that's all they're looking for in example E, is what is that explicit expression?
So that's it.
I'm afraid that's it. Should I make it more complicated?
No.
You're sure?
This is just a.
Okay, you're
Clarification.
good on that?
Clarification.
This is just clarification, yeah. Let me be clear, we're done here. Wait.
Where's the button?
Yeah, I gotta get the button out.
That was easy. I got
What is
it.
it, one?
Man,
Push me.
it's not here.
That
Wait a
was
minute, there it is, there it is.
Why you had to hit me so hard?
There we go.
That was easy.
There we go, beautiful. All right. Let's move on to example F.
I hit you 3 times.
So we're gonna do something similar for example F. My sequence this time looks like 2 and then 5/4 and then 8/9. 11/16 and 14/15. Now, sometimes that first term can be a little bit misleading.
Very.
And to maybe help you out a little bit, let me note for you that you can also write that as 2/1.
I should be a teacher.
All right.
Absolutely
All right, so this is our a sub 1, this is our a sub 2, this is our a sub 3, a sub 4, a sub 5. Our goal is to find a sub n. Now, one thing that we know is that it's going to be a fraction. Start with the denominator part first, and maybe look at these. You should see something that's kind of going on with those denominators. The numerator part's harder. And it'll be easier once we've gone through arithmetic sequences in section 12.2. Maybe some of you will catch it. I will note for you that each of the numerator terms is 1 less than a multiple of 3. So like 11 is 1 less than 12. 14 is 1 less than 15, etc. So it's 1 less than a multiple of 3. So there's a little hint there for you. But give that a shot. See if you can come up with it. If you're watching this later on YouTube, then fast forward a little bit.
Where's the X factor?
What's that? All right. Let's see. Are you guys coming up with a general pattern here? The numerator part should be easier than the, or I mean, the denominator part should be easier than the numerator part.
No, sure, we'll let it know later.
Well, look at the numbers. So what you should be doing is looking at the numbers. Like 2 somehow it leads to a 4, and a 3 leads to a 9, a 4 leads to a 16, a 5 leads to a 25. So what are you doing with these numbers to get from here to here? There's an operation there.
Write that as a subscript.
Aha.
Let's see, if you put in, try testing, put in a 1 there, or a 2, are you gonna get the terms in our sequence? If I put in a 1, 1 plus 3, 4, divided by 1 squared, it's like 12.
Oh, hold on.
So the nice thing about this is you can test it. You can check whether or not you've got it right before you hand it in. So let's take a look here. How about the denominator part? 2 goes to 4, 3 goes to 9, 4 goes to 16. What's the general term in the denominator?
A sub n squared.
Yeah, should have a squared term in the denominator. All right? And the numerator term, and I gave a little clue about, it's 1 less than 3 times a number.
So 3n minus 1.
3n minus 1.
Oh, so
The thing you should do is check it after you've done this. If you look back at it and try a few numbers, like if I put in a 4 here, 3 times 4 is 12, minus 1 is 11, over 4 squared is 16. You can do likewise with the 5 or the 3 or any of these things. That's why I said the 1 is a little bit misleading because you don't see that it has a denominator, even though it does. Yes?
do you just put n or do you put a sub n?
Well, this is a sub n. So I tried to write this as a little bit of a subscript. It's in a smaller font and a little bit below the line with this. So it is appreciated if you do take a little time here not to write it as an, all right? That makes me kind of unhappy. It should be a little bit more of a subscript there, okay?
I have a question.
I got an answer, what's up?
Good question. So why wouldn't it just be n plus 3?
That's what I read.
Because.
All right, let's try it, let's try it.
If it's already going up.
Let's just try it. Let's just try it. So the question is, why isn't it n plus 3? So a sub n equals n plus 3 over n squared. Let's list the first few terms if I did it this way. You're not alone in thinking that. So let's try a sub 1. That'd be 1 plus 3 over 1 squared is 4 over 1, or just 4. So that doesn't work. How about another one? A sub 2. 2 plus 3 over 2 squared is 5 over 4. All right, that one worked. How about a sub 3? So that's going to be 3 plus 3 over 3 squared, which is 6 over 9. That one's not working either. So, it works for 1.
I forgot you had to sub them in. I was just thinking because they all go up by 3. So like 5 plus 3, 8 plus 3, 11.
Yeah, so.
But I realized I see what you're saying. You got to sub A1, A2, and A3 in for the n. So it'd
Okay.
be like 3 times 1 minus 1. I get it.
Okay.
I hear what you're saying, 'cause that's what I'm thinking. So how do you get the 3n minus 1?
Well, like I said, the easiest thing to do is understand arithmetic sequences, and that comes in the next section. So if you're not quite able to catch this, I get it. The hint that I gave out was that this is less than, or is 1 less than 3 times the number. 3 times 1 minus 1 is 2. 3 times 2 minus 1 is 5, etc. So I did give out kind of a hint there, but this is an arithmetic sequence in the numerator part, and we'll be able to discern that pretty easily after the next section. So I wouldn't stress about it too much just yet. They will get a little bit easier to see there. Before I do example G, let's talk about alternating sequences. Alternating sequences. And I'm going to write down 3 of them. A sub n is going to be negative 1 to the nth power. B sub n is going to be negative 1 to the n minus 1 power. Now we'll do plus 1, and then we'll do minus 1 down here. C sub n is going to be negative 1 to the n minus 1 power. Now what I want us to figure out is a few things here. I want us to figure out the first 4 terms of each sequence. I want a sub 1, a sub 2, a sub 3, and a sub 4. And then likewise for B and C, I want B sub 1, B sub 2, B sub 3, B sub 4, and you don't have to necessarily go through all these by, grunt work calculation. You should pick up on a pattern really quickly as you work through these. Now I'll do maybe a couple with you to try and figure some things out. For instance, if I want a sub 1, that'd be -1 to the first power. That's just -1. How about a sub 2? That's -1 squared. -1 times -1 is +1. What happens when I cube -1?
It's gonna be negative again.
It's going to be negative again. So what's the overall pattern here?
It's gonna be negative, positive, negative, positive.
Negative, positive, negative, positive. Look through at the other two and see what patterns you get for those. All right. Nice. I wonder if that's going to be picked up by the audio here. All right. So, Johan, what'd you get for these numbers here?
Pass.
Brian? Man, nobody? Who's got this? Caleb?
It'll be one, positive one,
One.
and then it'll be a negative one, and then one, and then negative one.
And interestingly enough, if you put in a 1 here, what's 1 minus 1? It's 0. What's -1 to the 0 power? 1. Not 0. 1, -1, 1. So the thing that I want you to see here is that these two are the same. So it doesn't really matter if you use -1 to the n plus 1, -1 to the n minus 1, you're getting the same thing here. So the real difference comes between these two. So I would suggest you just use these two to make your series alternate. And that's what we need in this example G here, is we need these series to alternate. Let's take a look at example G, and we'll finish that up. And
So how does B to the 1 plugged into that equation equal 1? Just.
good question. Let's take a careful look at B sub n is -1 to the n plus 1, which if I want B sub 1, that's going to be -1 to the 1 plus 1. 1 plus 1 is 2. -1 squared is -1 times -1, which is a +1. If I had B sub 2, -1 to the 2 plus 1, -1 cubed, now I've got an odd number of negative signs, so I get a negative product. So it just it comes down to even or odd number of even or odd number in the exponent, and that's going to dictate if it's positive or negative.
I was multiplying that, I just did it.
No worries, no worries. I appreciate the question. Sure that there's somebody watching this now that probably appreciates that as well. So let's look at the actual problem for example G. Looks like this. Our series, or excuse me, our sequence looks like -1/3, and then 1/9, and then -1 over 27, and then +1 over 81, etc. our goal is to find the general term for this. Now, when you're facing something like this, don't try and do it all at once. Break it up into little parts. For instance, let's write a sub 1, a sub 2, a sub 3, a sub 4. I could rewrite these terms because there's an interesting pattern in the denominator. What's a different way to think of 9?
3 square root.
3 squared. How about a different way to think of 27?
3 cubed.
3 cubed. And maybe you're not as familiar with 81, but you can probably take a guess that this is 3 to the 4th power.
That's a little nice.
So let's see here. That gives us a lot to think about. A sub 1 has a 3 in the denominator. A sub 2 has a 3 squared. A sub 3, A sub 4, etc. The other thing you're going to want to think about is the fact that this pattern alternates. It starts out with a negative, then positive, then negative, then positive. Personally, when I do this, I start out by figuring out it's -1 to some power. And I write that in there, and then I forget about the alternating part of it after that. Now, it's your job to decide which one of these you want. Do I want this one, or do I want this one? Let's bring that down. Do I want this one or this one? Which one has the alternating pattern that I need?
The first one, so it'd be.
The first one. -1 to the n power. What's the numerator for all of these?
It'd be
1. And what should I write in the denominator?
I mean, it'll be 3.
It's not really written here, but it's understood to be a 1. 1 and a 1, 2 and a 2, 3 and a 3.
So it'll just be,
So is it?
Do it to the end?
3 to the n.
Oh,
And that's it. So you just break it up into little pieces. You don't have to attack the whole thing all at once. Now, when I looked at my morning class, when they did this, there was a lot of variety around this. Some people wrote it as -1/3 to the n, and that's fine. Other people wrote it as 1 over -3 to the n. That's fine. What I will be careful of is not to allow you to write it recursively. And you could write it recursively as -1/3 times a sub n minus 1. That's, that's on me if I don't say, don't write it recursively. But that's not really what I would be looking for in a problem like this, typically. All right, so you've got 1, 2, 3. I think there was 4 different ways that my morning class wrote this. Only 3 are coming to mind right now. Are you comfortable with this? So there's a question back here.
How does that first one, -1/3 to
It works. If n equals 1, this is just 1/3. If this is 2, you get -1/3 times -1/3. The negatives are going to cancel, and you'll have 1/3 times 1/3, which is 1/9.
I see.
So, yeah. Hannah?
In this equation, what does recursive mean? Like, is it like,
Recursive means it's defined in terms of itself. So this says if I have any one term, to get the next term, I'm going to multiply by -1/3. So if you look at this, you multiply by -1/3, you get this term.
you don't want the an in it?
So no, I don't want it recursively. Typically, the answers I'm going to look for in these types of problems would be these right here. Those are the ones that I want.
Because that one has an a in
So
it.
that's the one.
This one is defined in terms of itself. So, for instance, I could easily figure out the 10th term here, but to figure out the 10th term, I need the 9th term. To figure out the 9th term, I need the 8th term, etc. And it keeps on going and going and going until you get back down to the first term. It's a pain. All right. Any more questions or thoughts on that one? All right, I'm gonna split this video into two halves, so look for part two.